yesterday, we had our first beginner-friendly paper reading group. So again, if you go to the Weights and Biases forum, so this is where I am. If you just search for community, by the way, everyone can see my screen, right? So I'm not doing anything wrong. If you could please just share in the chat, that would be wonderful. Okay, perfect. So if I go to the community.1db.ai, just that link, I'll paste that in the chat as well. So if I go to that forums link, then you'll see, so now we're at that stage where the Fastbook Reading Group and the paper reading group are kind of very at that point where they both kind of collide with each other. So if I go to paper reading group and I go, there's two, you'll find these two threads, which is ResNet. So just as of yesterday, we discussed the ResNet paper in detail. So we went through the whole paper, we looked and read the research paper and kind of understood what's going on in the ResNet architecture. And there were a few people from Fastbook who attended that session, so I'm really happy for those that did. And kind of now my appeal to everybody who's been part of Fastbook is this. Now we're at that stage where we can all start reading papers. We already have a good platform set. So this is kind of how my journey also started, or this is how I kind of progressed in my journey as well, is like Fast AI gave me that solid baseline and that solid platform. And then after that, I started reading papers. I started trying to code a bit more things from scratch. And this is how then you just start developing things on top and you start developing that knowledge. And I think that's the same advice that I would have for everybody who's part of the Fastbook Reading Group, is that now you're at that stage where you can start reading papers. And something I do want to point out is the next Wednesday, so Wednesday, Wednesday 15th, not next, but just the coming Wednesday, the 15th, what we're doing is we're doing ResNet live coding in PyTorch. So something I'm gonna do today, we're gonna look at ResNet and we're gonna look at ResNet in Fast AI, and we are going to code it from scratch, but then we're still using the Fast AI framework. And something I do wanna do on the side as well is that I wanna take the Fast AI folks to the paper reading groups and then also like show how these things can be done in pure PyTorch. So then that just helps with the, when you do things from scratch, like PyTorch is like this scratch, Fast AI is this layer on top that makes things a lot easier. And then you have these papers. So you could implement the papers in Fast AI, you could implement the papers in PyTorch. But I think if you can do it both, that's where you understand everything about everything there is to know about a particular training loop, a particular paper. So this is something I want to try in like between our paper reading groups now. We will have these live coding sessions where I'll be live coding things from scratch. It will be it won't be as perfect because it's a live coding session, so I'm never perfect when it comes to live coding, but I guess that's the point. Like you'll see me making errors, and when you do see me making those errors, you will also see me how I try and fix those errors. So I think that will help everybody in their journeys when you also hit similar errors in your when you're trying to replicate things from scratch. And so to summarize, I guess please start reading more papers, and then we're also doing these live coding sessions that will help you. As usual, as every week, if you go to 1db.me/fastbook14, so let me go 1db.me/fastbook14. So that brings me to this discussion thread for today. So we're going to have all our discussions today. Somebody's already typing. Great to see that always. So everything that we discuss in our paper in our Fastbook reading group today is going to be in this thread. Angelica's already added the blog post from last week, and then we'll add links from this week as we go on. So this is how like we've been managing the Fastbook reading group. You'll see like there's a week 11, week 12, 13, 14, and so on. And then there's a weekly discussion master thread that you can see where all the other weeks are. So I think that's really helpful and really nicely structured, and we should make the most of discourse. So I'm coming back to week 14, and this is where we'll start our journey on ResNet. Something I'm really excited to see, and Ravi Mashru and Vinayak, they've been, and even like I think Ravi Chandra and Niyasi, like you've all been blogging week after week, and something I'm really excited to see. I'm sorry if I missed the name, but it's not so much to highlight like the name, but just highlight the work and the effort. So something I'm really excited to share and see week after week is that Ravi Mashru has been coming in and he's been writing wonderful, wonderful blog posts about fast AI. He's been writing wonderful blog posts about everything that we've been doing week after week. And I'm seeing more and more that Jeremy started retweeting Ravi's tweets. And that's really like, I was talking to Ravi today and he said it's like a fan moment for him every time Jeremy retweets his tweet. And I can completely relate to that because I think that's how I felt when Jeremy retweeted my tweets for the first times or the earlier tweets. So I think, oh, sorry, I pressed something. So I think that's really, really nice to see that how Ravi's journey has progressed. And he's at the best thing is like he started reading papers now. So he's already written about the one cycle LR. So we keep talking about one cycle LR. We keep talking about what it is in fast AI. But he's actually went in and he's written this really nice blog post about understanding superconvergence. And you can find the link of those. Sorry, I shouldn't have pressed that. That was weird. I could hear myself. So you can go in and you can click this Ravi Mashru's post on superconvergence. That will take you to that blog post I'm highlighting. And Vinayak, again, similar journey, very similar path. And I'm so excited to see that he's also grown and he's also like, just reading his blog post, I see a lot more detail. I particularly love like how Vinayak has these handwritten notes. I used to have them on iPad, but he's come up and like put them on paper. And it's like, it's really nice to see. It's a really good feeling to see like what worked for me is kind of working for others too. So it's really, really nice to see that happening to both Vinayak and Ravi Mashru. And again, Jeremy's been retweeting Vinayak's tweets as well more and more, which is perfect and which is like the best outcome you could expect. Because if Jeremy's highlighting your work, then it's got to be good work. So that's how I would say. Like if otherwise, yeah, like I mean, now you're like writing those blogs that are helpful to more people, and once you start getting at that stage, you're just getting better and better at your craft, which is wonderful and which is all that we expected when I first started and when we first started the Fastbook Reading Group at Weights and Biases. So again, I really like these Microsoft Excel explanations, and I really like these handwritten notes. So thanks Vinayak and thanks Ravi for doing this week after week. Okay, so now going back to, I will answer this. So we're just going to get started with ResNet today. But let me just quickly have a look at this question. Is it recommended to dedicate some time learning framework or try to find repositories from papers with code and use Stack Overflow? Asking this because I'm not good with coding part of ML. Also, should we follow PyTorch Reading Group? A lot of implementation of old papers are in TF. How to go around that? Okay, I'll go one by one. So do you want to find repositories with papers and code? If you're starting fresh with reading papers and you want to see how they're implemented in code, so I think starting with ResNet would be a great point. But also, again, I'm not like, this is not just, I know I'm a little biased in highlighting my own work, but I do feel it's going to be really helpful because when I started, things like this didn't exist. Like I didn't know anybody doing live coding sessions on papers. And like there were still groups that did discuss papers, but there weren't any groups that would show how things are written from scratch. And that's how kind of even my own blog picked off. Like that's how my kind of blog was so different from the others, is how I had code for every piece of paper or every section of the paper. And again, this is something that will be really helpful to those starting and to those who are beginners and want to start reading papers, is that from this week onwards and from the ResNet, basically we're starting with ResNet because that's what we'll discuss today. But from that, we're going from ResNet to DenseNet, then we're going to go to EfficientNet, then we're going to go, like, we're going to keep leveling up. So I would really, really recommend all beginners, like if you're new to coding, start here. And then from there on, you could find papers that already have implementation. So I think the next great place would be TIM, PyTorch Image Models. So if you can see PyTorch Image Models, TIM is here, and then you can go TIM, you can go Models, and then you can see the implementation of like so many different models over here. Like you can see ResNet, you can see ResNext, you can see SENet, and then again, there's like lots of these different resources that could be followed. But this again is a great place to get started. And then what were the other questions? Is like, should we follow the PyTorch reading group? 100%. I think being a good deep learning practitioner is all about like being a good coder as well. And in that PyTorch reading group, you'll understand the basics about PyTorch. And when we go to these like live coding sessions and we're going to start doing things from scratch, and we're going to start building those training loops from scratch, and we even Fast AI is built all on top of PyTorch. So like if you want to understand and dig deeper into Fast AI, we need to know PyTorch. So I think that would be really helpful if we, if everybody got a good understanding of what PyTorch is, if everybody got a good understanding of like tensors, good understanding of training loops. And again, we're here at Weights and Biases to help you along those journeys. So yeah, so keep following along, and we will keep sharing more resources. And then a lot of implementation of old papers are in TensorFlow, how to go around that. So again, there's different ways to go about it. So I think I will share, there's one on ResNet RS. I think there was a pull request that I once made on ResNet RS to Tim, to PyTorch image models. And something to highlight is like, the more proficient you get at one framework, the better you're becoming at the other framework too. Because it's not like PyTorch versus TensorFlow. So if you understand the basics of like, okay, we're gonna a basic training loop consists of like getting a model, getting the output activations from a model, calculating the loss, doing the loss step backward. And once you like start understanding how these things are done in PyTorch, you're automatically understanding those things in TensorFlow, because then all you have to do is just understand the syntax. And same for like, okay, if you understand what a convolution is, how you implement a convolution in PyTorch, or how you implement basically any architecture in PyTorch, you'll also have a better understanding of things in TensorFlow. So when I was first, I'll share an example. When I was first doing ResNet RS, we did a paper reading group on ResNet RS as well. So if I go here and I go paper reading group, I go master biweekly list. I think there's a ResNet RS somewhere here. There isn't. Okay, because we didn't live stream it on YouTube. I remember. But anyway, when I was doing the ResNet RS paper reading group and I was reading that paper for the first time, the implementation and the weights were in TensorFlow, but it wasn't much of a problem because I understood the basics of it. And so when I went and I started looking at code in TensorFlow, it was just very easy, and it was still an easier part. And I hope that as you get better in PyTorch, you're also getting better in TensorFlow. So I hope that answers like all three questions that have been asked. Great blog posts. I saw Ravi's. Thanks, Aman, for highlighting, and thanks for the high quality work. Yes, that's lovely. Thanks, Kevin. And again, okay, there's more questions. How about I'll come back to these questions in say a while, because I'm also conscious of time, and we want to wrap up. We want to wrap up ResNet today as well. So I'll come back to these questions on the forums. Okay, so we are at ResNet. So the ResNet YouTube video on the paper for the paper reading group that we did yesterday should be up very soon. I think that would also be a really good place to get started with ResNets, because it's mostly going to be a repeat of what we discussed yesterday, but I'm going to try and like include all the information needed in today's session as well. But I would highly recommend for everybody doing the session today, please have a look at the ResNet paper reading group YouTube video yesterday, and we will share that link on the forums. So okay, so ResNet. So then ResNet again, most of this is same. So deep residual learning for image recognition. That was the paper that came out in 2015 by Microsoft Research, and Kai-Ming He has been he's been like a pioneer, and he's been at the top of like so many nice research papers that I love, including like some of them were like excuse me. Some of them were like focal loss or just others like but I think sorry yeah so I think these papers have been wonderful. Like ResNet is the most used model architecture, and I showed a fact yesterday like that ResNet has been cited 75,000 times, about 74,500 times. So you can imagine how impactful this paper has been. And you can imagine like how much the impact this paper has had on the computer vision field in general. So like all the recent papers that have come out have kind of built on top of ResNet, and until we've gotten to a point here today that even like you could even compare Vision Transformer in some ways to ResNet, because even that is using skip connections and all of that. So like there's really a lot of good things that have come out from the ResNet paper, and we're discussing that today. So going back to ImageNet, ImageNet was that smaller subset of the ImageNet that we keep talking about. So this is just getting the data, untying the data and creating a data block. I'm not going to go into the details of this function because we've looked at this many, many times. So this just gets the data, creates the data loaders, and I could click, I could press dls.showBatch. So dls.showBatch shows like these 4 images with 4 categories. So this is what we have to do. In this case, we have 10 basically we have 10 categories, and also we're using like 128 by 128 pixel sizes, because when we said, I think we said somewhere, oh, we're using ImageNet 160, but we're using a size as resize. So see, the size being passed here is 128. So we do pre-sizing at 160, then we do the data augmentations, and we resize every image to 128. So we're using 128 by 128 image sizes in this. I will continue skip through most of this, because if you remember, like in MNIST, we got to a point where the final grid size was a 1, and then we just flattened it. But imagine if we start doing that to like, let me highlight what we, let me bring that up in OneNote quickly. So we had like a MNIST, we had 28 by 28, and when we did a convolution, right, the size got down to 14 by 14, then it got down to 7 by 7, then it got down to like, I think it got down to 4 by 4, then it got down to 2 by 2, until it got down to 1 by 1. So like for each image, then we had kind of like just the 1 by 1 output, which we could then flatten to see like, okay, what are the class outputs? So that's something that we did in when we were doing MNIST. But imagine like if this size is say 128 by 128, you would need a lot many of these convolutions, about like, you would have to keep going half and half and half. So it's 2 to the power 7, I think. Yeah, I think 128 is 2 to the power 7. So instead of like needing just like these 4 or 5, you would probably need 7 or 8. And if you go even bigger size, then that's even more, and so on. So if you go 512, then you can see how like this is a problem. So one thing you could do is we could use something called average pooling. And what average pooling does, this is really interesting, is that, so what average pooling does, like the problem is now, what you want to do is you want a network, basically you want your network that can take 28 by 28, or it can take 128 by 128, or it can take 256 by 256 as input and still give me like 10 outputs, right? Why 10 outputs? Because you have 10 classes. So you need something like that, right? So if you pass one image of any of these sizes, what you need is a network that can give me like 10 outputs, which you can then do softmax, and you can check, okay, what is the probability of like this image belonging to one of those 10 categories. So that's what we want to do. And to do that, you can't really have a network architecture like this, because if you pass something, because right now you're after 4 convolution layers, you have 1 by 1 output. But if you have like something like 128 by 128, you would need 7, which means you can't really pre-train the network, which means you can't really pre-train this network with ImageNet, and you can't really use those weights. So you need a network architecture that has the same structure. So you don't want to change the structure or the architecture of the network every time there's a new image size. You need a network architecture that can handle multiple image sizes, right? So what you do, there's something called global pooling, average pooling, or max pooling. Basically, it's called, it's just basically called pooling operation. So what you do in this case is, let's say you have a network, right? And you input 128 by 128 image, right? And this gives you an output of, say, 128 channels by, so this is, say, 3 channel by 128 by 128. And remember, as we go down the network, this is something we discussed in our last chapter, is like you keep increasing the number of channels and you keep decreasing the number of basically the spatial dimension. So maybe you get like 128 channels and you get, say, I don't know, 14 by 14 maybe, right? So let's say you get something like this. Okay. But then again, if you get, say, again, if you have something like 256 by 256, 3 by 256, the same network would now produce an output of 128 channels, but this time, instead of this being 14 by 14, it's going to be 28 by 28, right? Can you guys guess why it would be 28 by 28? Like why it would be, I guess the question is why it would be double of 14. The answer is because the image size is double of 128. So if the image size is double, then the output size changes. That's what a convolution does. Remember what a convolution was? A 3 by 3 convolution, if you have an input of, say, if you had an input of, say, 128 by 128, it gives you an output of 127 by 127 if it's not padded. And if you had like 256 by 256, then it gives you an output of 255 by 255, and so on. So like in the convolution neural networks, the output size is different based on the input size. So now what you want is you want to take, like, you want to be able to take both of these and you want to still be able to classify them into 10 layers. So what you add is you add a pooling layer after pooling layer. You add a pooling layer. So what does this pooling layer do? It just takes the average on the second and the third dimension. Because remember, the first dimension is batch size. So you're gonna, the 0th one is batch size. So you're gonna skip over that. So what it does is you take the average of these spatial dimensions. So if you look at this output, it looks something like 14 by 14 and 128 by 128, right? So what you do, this is 14 by 14, right? You could just take the average, then it becomes one number. Then you could just take the average of this part, it becomes one number, so on. So you get a 128 long vector, right? The same thing you do for this one. You have something called 28 by 28 all the way to 128. So you have 128 channels and 28 by 28 as my spatial dimension. So then I could just take this, take the average, 1 pixel, and so on. So you get, again, a 128 long vector here as well. So now you're getting the same output because of this pooling layer, irrespective of the input size. So what you can do now is, like, now that you're getting 128, you always know that you're going to get an output of 128 long vector length, irrespective of the input image size. You could just have an nn.linear in the end that goes from 128 to however many your classes are. So you could just go from 128 to 10. So then every time for every image, you get 10 outputs. I hope this is clear, because this is a really, really important part. And if this is clear, then we're at that point where sorry, just guys, just give me one sec. Okay, I'm back. So question, using global pooling allows you to use any image size as input. Yes, that's correct. However, during training, is the network going to perform better at particular image size? Yes. So it's like, that's a good question. So different networks, depending on like how many data set sizes you have. So if you have like 10 million, like ImageNet starts with 2 to 4 by 2 to 4, but it's not to say that it won't work better on 348 by 348 or 512 by 512. So I think it just comes down to like trying different image sizes, but generally the bigger image size you go, the better it is. So you start with, say, 2 to 4 by 2 to 4, then you go 384 by 384, then you go 512 by 512. And this is this idea of progressive resizing that we discussed before as well. So I hope that helps. Okay, so all of that just to explain this one line of code. Wow. so now you know like why we have this average pool. So what you can do, basically this idea of like pooling or taking the average in PyTorch, this is just called nn.adaptive average pool 2D. So you can see, so if you search adaptive pool average 2D, you can see like applies a 2D adaptive average pooling over an input signal size composed of several input planes. The output is a size h by w for any input size. So that's the key point. So like if you have, I'm just going to check. Yeah, so I'm going to skip over that, but go through the documentation. I think it will be really clear on what this does. But you can say like if you say 1, that just means that it's going to flatten my input image size to basically be that 1 by 1 pixel, and then you can still apply the flatten after. So let's to basically make things more clear. You could actually now go through this network 1 by 1, and we could actually step through this network, and we could check what the output image size is. But I'm going to skip over that now. But the thing that I'm trying to say is like create this network, like say class model, and it's an nn dot module. So I'm just, this is where I'm saying this is where the knowledge of PyTorch will come in handy. So you could just say like define dunder init self nothing, and then you could create like self.blocks equals this. And you could say self.pool equals nn.average pool. And then you could say self.linear equals nn.linear 256 by dls.c. Okay, and then I could just create my forward. I will explain what I'm doing, just give me 1 sec. And you could say out equals self.blocks x, and then out equals self.pool x. Oh, this should be out, and then out equals flatten flatten out. Is that how that would work? Let's see. And then out equals self.linear out, and you return this out. Okay. So let's see if that works. So let me just quickly go through that. My input say is torch.random. So I'm just creating a random input of say 128 by 128. So this just means single image. So I've basically just I've just tried to replicate this model just using like a more classical approach of defining this as a nn.module. So I just take my input, I define my model as like that, and then let's see if this creates an output. It doesn't. Block is not defined. Of course it's not defined because it's defined in this. And it says there's another problem. It says cannot assign before module init call. So what does that mean? Cannot assign block 128, and it's giving me an error here. Oh, because I didn't do super.init. Okay, how about that? Oh, there we go. See, that works. So now what we could do is I could just create a breakpoint here. And now if I do that, I can check what my output shape is. So you can see, so you have basically what you have here. What I'm trying to show you is like just a way to do these experimentation, and just a way to like do these different things is you could actually have like, I've just broken down this whole network into like, I broke it down into blocks being at the top, then having the average pooling, then having the flattened layer, and then finally the linear. So that's how my outputs are going through. So I could put a breakpoint after the blocks, because like this is just saying that my network is always going to be like this. Like there's no change in the network. Remember, my network is the same. The only thing that changes is this output size, right? Based on the input image size. So I just wanted to show that in practice. And that's why I've put this breakpoint. So I could now go, if I put that breakpoint, you can see like if my input is 1 by 3 by 128 by 128, the output is 1 by 256 by 4 by 4. And what happens if I pool it? So let's see the shape of that. And you can see now it's 1 by 256 by 1 by 1. So it's doing the exact same thing that I've just explained to you. It's now taking like, it's now going to this, instead of this being like 4 by 4, oh, sorry, what did I press? Something. So if you have like this 4 by 4, it just makes that to be a single pixel because you just take the average and you just do the same thing for all of those planes. So I hope that makes sense. And then I could just update my input image size to be 256 by 256. And now let's check what my output shape is. So instead of it being 1 by 256 by 4 by 4, this time it is 1 by 256 by 8 by 8, just exactly as I've explained here. And then what you could do next is you could now still, if you take the pooling, you check the shape, you can see how it's now 1 by 256 by 1 by 1. So it doesn't matter what the input size is. What I want to say is like this pooling layer, sorry, give me one sec. So what I want to say is like what this pooling layer does is it makes sure that your output, irrespective of the input size, is then just flattened, or sorry, it's just then you just take the average and you always get like this 1 by 256 by 1 by 1 output. So I hope that is clear. So you can see if I remove that breakpoint, you can see I'm still getting it. It doesn't matter now what input image size I pass in. So you can see I'm always getting like 10 outputs for my one input image. And if I pass in, say, 10 images, I get 10 outputs for each of those 10 images. And if I passed in, say, one image, I don't know, any different size, you could just go 1024 by 1024, and this model will still work. And the reason why this model works is just because of this pooling layer. That's the magic. So let me see if there's any questions about this. Yes, that's a great point. Definitely, if you're using pre-trained weights, most of the images have been trained on 2 to 4 by 2 to 4. Sorry, most of the models have been trained on 2 to 4 by 2 to 4 on ImageNet. That's the image size you want to start with, and then you could just increase it to be 384 by 384. But another trick is called test time. I can't remember the. I think it's called fix ResNet or something. Basically, what you do, fixing the test time resolution. There's another this paper. There was one of those. Yes, there it is. Fixing the train test resolution discrepancy. Yeah, I think this is where they basically increase the image size during inference. So you train a model on 2 to 4 by 2 to 4, and then you inference the model on 256 by 256. So that's something I want you guys to try. I'm just going to put this. Please try this. Train the model on 2 to 4 by 2 to 4 and run inference on, say, 384, 256 by 256. Try this out. For those of you still participating on Cassava, try this simple technique out. It might work. Okay, so that's that. So I've just explained what pooling does. I haven't gone much into detail into ResNet yet, but we could now just pass that model to a learner. I could grab my learner. I could say learn.lrfind, which will give me my, basically it will give me the learning rate that I should use. Then we can pick up the learning rate from this, from that architect, or from that curve. And you can see like you want to pick either the steepest point. So we pick 3e neg 3, which is somewhere here. That's completely fine. And we say learn.fit one cycle, and that will train. And that's it. So we just trained a neural architecture. Until now, we haven't really trained a ResNet, because in ResNet, as some of you might know from yesterday, the trick or technique was that there was a skip connection. So that's something we're just going to discuss next. But are there any questions for me? Thanks for sharing, Kevin. Cool. Looks like there's no questions so far. So I'm just going to assume everybody understood what I said. Is that correct? Okay. So now what's next is, now we're ready to start creating a ResNet. So as most of you might know from yesterday, basically before ResNet, training deeper architectures or deeper layers was really hard. So a 20-layer network did better than a 56-layer network. And like there was this idea of like there was these different problems. One of the problems was a vanishing gradient problem. One of the problems was a degradation problem. And again, these are things we discussed in the paper reading group yesterday. But Fastbook, as part of Fastbook, I won't go into all the details of the paper, but some of the details were like there were problems before ResNet. And then what ResNet tried to do is it tried to fix those problems. And in trying to fix those problems, what it said is like, until now, you just have your input, which goes through the network, and then you get an output. What if you added an identity layer? So what identity layer means is like you take the input and you add it as is to the output. So instead of like having something like, if in mathematical terms, instead of having my output as f of x, you have the output as f of x plus x. Again, this is something that I explained in a lot more detail in the paper reading group yesterday. But I've just repeated that bit just so it's easy for everyone to follow along today in case you didn't join the paper reading group. So again, this is the idea, like you take the input and you just add it to the output. So you get your output is like f of x plus x. So you can see, I won't go up, but basically, as you can see, in this network, you just have block after block after block. But you don't really have any skip connections, which is this part that adds the identity. So having those skip connections is what was the main idea behind a ResNet research paper. And then you can see now we can create like my ResNet block like this. So what this does, what's a conf layer? Let's have a look. So a conf layer is a FastAI. It's implemented in FastAI layers.py, and it creates a sequence of convolution, number of input channels to number of final channels, and then ReLU, and then norm if there is. Okay, so it's basically conf batch norm ReLU. It's basically just that block. It's just like a conf layer just implements conf batch norm ReLU, right? So let's see. You either have batch norm, then you init your batch norm, then you create your convolution function, and you add them to the layers. You add your activation batch norm if there is any. If you're using instance norm, then you add instance norm instead of batch norm, and you add that to your layers. You add them to extra. So extra, is that an nn.sequential? Where is extra? Oh, this is already an nn.sequential. Okay, that is great. And it delegates nn.conf2d, which is all good. And you go super.init layers. I got it. Okay, that's really helpful. So can you see what's happening in this piece of code? Basically, what's happening, actually, instead of doing this, I should have probably gone doc, right? Doc or docs? Doc. I should have gone here. I should have clicked on that, which gives me, and I should have clicked, actually, sorry. I should have clicked on this, and then I should have clicked on show in docs. So it'll take me to the FastAI docs, and you can see like all the things that Conflair can do. And you can see more examples on what Conflair can do. So I think it's really helpful to then just go through. I won't go into the much details, but for those interested, just go through this layer, go through the documentation, understand, look at the source code. But essentially, it's just creating a conf batch norm ReLU layer. That's all it is doing. So what we can do is we can create our two cons. See how you have in ResNet, you have first weight layer, then you have ReLU, then you have the second weight layer, but you don't have a batch norm after the second weight layer. So what it's doing is like it's creating your first layer going from number of input channels to number of final channels, and then it's creating the second conf layer, which is going from number of final channels to number of final channels, and then you finally set up the norm type as batch 0, which just says, okay, please don't set up batch norm. So this is where it goes. Where norm type equals this causes FastAI to init the gamma of the weights of the last batch norm layer to 0. That just means like it's going to make every time you multiply in batch norm, remember, you're just trying to normalize things. So it's like, I think, I can't remember the exact formula, but it's like x star gamma plus beta, something like that. I can't remember exactly. But basically, you just init that to 0 for your second layer. So that's that. But the problem with this conf is, again, it can't handle a stride other than 1, and it requires that ni equals nf. Can you guess why? I will ask, like, oh, sorry. So let me show you. Actually, the best way to like understand these things, and like I'm not someone who understand things in theory better, but I'm someone who understand things in code better. So what I'm going to do is I'm just going to create a res block which goes from 3 channels to 32 channels. And then what I could do is I could pass in my block. I create my input as, and then, oh, sorry, torch random 1, 3, 128 by 128. And then I could pass in this and I could check the shape. And it's giving me an error. The size must match the answer of at non-singleton. Of course. So I gave you a hint. Just by doing this simple example, I gave you a hint on why the number of input channels needs to be equal to the number of output channels in this case. Can you guys guess why? And I'm just going to see, is const background value a standard? Yes, it is. It's definitely a standard. It's like the standard block. You have const background value, then you have another block const background value, then you have another block const background value. So every time, like when I say in a deep learning network, you have like these layers after layers, so on like that. Mostly like this standard thing is like a const background value, and like in ResNet, each block consists of like there's like 4 blocks in ResNet. So this is the first block, third block, fourth block, and for ResNet, I think 34, it's 3, 4, 6, 3, which means you have 3 const background value, you have 4 const background value, 6 const background value, and then 3 const background value. So that's just like different versions of the ResNet architecture. But const background value is pretty much the const background value is pretty much a standard, Ravi. The reason you need the input and output is for the identity addition of the input. Absolutely. Thanks very much for answering that question. So if the so if I go, so look at this, right? If I go to say if I want my rest block to go from input channels 3 to 32, then what's that going to do? When I do self.const x, that's going to be, the output is going to be of 32 channels, right? But my input is still 3 channels. So I can't really add the 3 channels with the 32 channels, which is the error that we saw before, which says the size of tensor 3 must match the size of tensor B with 32 channels. So it's basically saying like, this is my tensor A, which has 3 channels, and this is my tensor B. The output of this is tensor B, which has 32 channels. So you can't really add them. So that's the reason why you need to have the same. And similarly, you also need to have the same stride, because if you change the stride, because remember, my input is 1 by 3 by 128 by 128, right? And if you remember what stride and what pooling and what all of these operations were, which we've discussed in our previous chapters, then what stride did, stride would go like, instead of having a single stride, it would jump and it would have a double stride. So if I made this a stride 2 const, so if I did stride equals 2, then what's that going to do is like, instead of my output being 1 by 3 by 128 by 128, the output's going to be 1 by 3 by 64 by 64. So let me run this, and you can see it gives me an error again. It says the size of tensor 128 must match the size of tensor B, which is 64. So you can see how you can't really have stride 2, and you can't really change the number of channels. Why? Because we haven't added pooling layer to this yet. So I hope like everything that I've explained so far now fits in and like kind of comes together, is like, this is why we need pooling. Because what pooling will do is then it will like, instead of like, we could just not worry about these things anymore, and pooling will help us with these things. So I can say here's a res block using this fix. So you can say these are the 2 issues that I mentioned, like this particular res block, which adds, so this particular res block is just a copy of this one. The first weight layer is this conf layer, the second weight layer is this second conf layer, and then what you do is you take the output of self.const and then you just add it to x. So you see your input goes to the weight layer, then goes to the second weight layer, so you get some output, which is f of x, and then you just add x to f of x. So I could just have, so this self.const of x is my f of x, and this is just my x. So I'm still doing x plus f of x. I hope that explains things. You would have to use interpolate to reline them up. Yes, that's generally the idea. Like you do want to interpolate them, but there's like different ways. You could use average pooling with a bigger grid size. So again, that's something that I will get into. I will explain that what's happening there. Just give me a tick. But are there any other questions? Are there any questions on like what we've discussed so far and before this? Because it's really important in understanding ResNets that we go step by step. So here's a REST block. So it says to fix this, we need to change the shape of X to match the shape of self.const, correct? Because let me actually call this as f of x, right? So f of x is this. And I'm just going to, all I'm doing here is like I'm making this look exactly like this, right? So can you see now how both of these are the same? So I'm just going to call this actually. Let me call this self.weightLayer1. I'm just trying to make this exactly as the image. So I'm just going to make this self.weight layer 2. And like these are things you could do as well, because I think it really helps with the understanding. Self.weight layer 2, self.weight layer 1, and you have x, and then you do this. So let's see, does that work? Yes, it does. So see what I did? I just kind of restructured my code so the code matches exactly this image. So I just created a self.weight layer 1, which is this conf layer. I created my self.weight layer 2, which is that conf layer. And finally, my f of x is this output from the two weight layers. So f of x is what? Self.weight layer 1, which is this output. And then you do the output to the self.weight layer 2. So you get your final output, which is f of x. And your final result that you return is x plus f of x. Now, what you could do is you could add stuff like print. Like I know it's really, really bad to use print here, or like print in a forward. Please don't do it anywhere outside, and don't tell anybody that you learned this from me. Don't take my name, because it's really people will kill me. But what you could do, just the easiest way that I do, is just do like f of x shape is f of x dot shape, and then x shape is x dot shape. So now you can see it's telling me that for the input, when I go 3 by 3, my f of x shape is this, and my x shape is this. So I can add my input to the f of x. But when I go 3 by 32, it's telling me my f of x shape is 1 by 32 by 128 by 128, but my x shape is 1 by 3, so I can't really add them. Or if I go stride equals, I'll just add this another parameter called stride, so I can pass it. And if I say stride equals 2, now you can see why this is a problem, because my input was 128 by 128, but my f of x is 64 by 64. So what we need to do is like, we need to make sure before adding x to f of x that both x and f of x are of the same shape. That's essentially all I'm trying to explain here. Okay, so I'm just going to call this stride 1. So this is exactly that's been mentioned in this part here. To fix this, like to fix all of these problems, we need to change the shape of x to match the result of self.const. Like we can't really half the grid size or do all of those things. So in that case, what we could do is we could create an updated REST block that looks something like this. You create your self.const as your conf block, right? you have your basically in your if the number of channels is different. Actually, let me try and explain this in here. So I have, say, my input 3 channel 128 by 128, and this is my conf layer. So you have your input, and then this is my skip connection, right? And you want to be able to add both of them. So if this becomes stride 2, right, then my output becomes 1 by 3 by 64 by 64. I hope there's no confusion like why stride 2 does 64 by 64, because stride 2 is basically, when you're doing convolution with stride 2, it's just skipping one step. So instead of like getting the same output as 128 by 128, you get half the output. And this is something we discussed in our last chapter. So now you can't really add this to 128 by 128. So what you could do is, to your skip branch, you could add something called a pooling operation. So you could have a pooling operation that averages a 2 by 2 grid to give you 1 pixel. So it averages a 2 by 2 grid to give you a 1 pixel. So when you average 128 by 128 using this pooling operation, you get an output of like 1 by 3 by 64 by 64. And then you could add the 2. So let me show you that. Ignore this for now, because that's not something we are worried about. So see how I'm like, I constantly change and update code. Like, I don't take the code as is. If I want to increase my understanding, I'm constantly changing the way I code. So you have your conf block, and now let me create my block as res block, and I could pass in, say, 3 by 32. Actually, let's keep it 3 by 3. My input again is torch.random. I know today is a slightly bit more complex than all the other ones, but I hope I'm able to explain it in a way that doesn't look that complex. So you can see my output now, like, it's able to add both of these up. So I'm just going to call this as f of x again is this, and now my shortcut output, or should I call it skip, is this. And what I'm doing is f of x plus skip instead of f of x plus x. Okay, this should be like that. Cool. So now what I can do again is use that stupid print statement, which I shouldn't have, which you shouldn't do it publicly outside of here. So, but feel free to do it in Fastbook. I can just say my output is this, and I can say my skip shape is skip.shape. Now you can see, okay, for 3 by 3, you're getting like my input shape is 1 by 3 by 128, and my output shape is 1 by 3 by. But what happens if I pass now stride equals 2? Okay, in that case, the f of x shape becomes 1 by 3 by 64 by 64, and my skip shape becomes also 1 by 3 by 64 by 64. So we fixed this problem, remember? So if I had, if I did the same thing with this instead, this was a problem, right? Because my f of x output was 1 by 3 by 64 by 64 anytime I did a stride 2, and my input was still 128 by 128. So to fix that, all we did was we added a pooling operation. That's it. And in the pooling operation, when we say nn.average.pool2d, stride, or basically we just pass in 2, because that's what the stride is in this case. What that's going to do is, like, it's going to make sure, so if you have what that's going to do is, like, if you have an input of 128 by 128 and so on, it's going to go through like 2 by 2 blocks and just create 1 pixel, 2 by 2 blocks and just create 1 pixel, 2 by 2 blocks and just create 1 pixel. So in the end, what you get is you get a 64 by 64 instead of 128 by 128. So now you can add the two together, because you're doing pooling on your skip, so you can add them two together. And now, so we fixed the one problem. So we had two problems, right? One, that the channels had to be the same. And the second problem was that the stride had to be the same. So we've just fixed the problem with stride by adding this pooling layer. I'll go and check again if there's any questions. No questions yet. So then the next problem that we have to fix is the number of channels, because right now, even with this implementation, I can't go from 3 to 32, but it's going to give me an error. It's going to say, oh, the channels. So see how this is the problem. Just give me one sec. Skip f of x plus skip. So it's saying 1 by 3, but why is this not 64 by 64? Sorry, one sec. Oh, it's still, oh, because I didn't. Oh, my bad. I should just do this and now that. Okay, that's fine. So I still can't go, ignore what I did now, but I still can't go from like 3 to 32 channels in this res block, right? I can't still have the different number of channels in this block. Like we're still trying to replicate this ResNet block, but even in this block now, I can't have like a different number of channels in my output than the input. Why is that? That's because if I do that, the output is 1 by 32 by 64 by 64, but the input is still 1 by 3 by 64 by 64. So even though we fixed this stride, we still haven't fixed the being able to like change the number of convolutions. So, so the first thing that we added here was pooling to fix the stride. And now what we want to do is we want our channels to be like 32 or some different number of channels. And for that, what we're going to add is conv 1 by 1. And what conv 1 by 1 will do is you can use it to change the number of channels. So instead of like you have your input, you have your f of x. So you get your f of x. And instead of your identity being just like that, you add two things to it. The first thing that you add is pooling, and the second thing that you add is conv 1 by 1. So now this is something that can deal with a different number of channels. It can deal with a different spatial size. And if you don't have different number of channels, if you don't have stride, then you don't add this to your skip connection. So see how it's doing this. So now I can add self.idconv, or should I just call it self.skipconv? Is a no operation if the number of channels are same. Otherwise, you go conv layer of 1 by 1 kernel, and you just update the number of channels. So I could just do my skip now becomes self.skipconv output, and now I should be able to add them two together. So, and there we go, that fixed it. Now my f of x is 1 by 32 by 64 by 64, and my skip shape is also 1 by 32 by 64 by 64. So now at this point, this is something that works perfectly well. Let me paste this in the forums. There you go. So what's the question? Sorry. If the number of channels is different, we could also have concatenated x instead of using and adding them. But if you're concatenating them and you're not adding them, then you're not really following ResNet, right? And what ResNet does is it adds the inputs to the outputs. So by concatenating, you're actually doing something completely different than what we're supposed to do. Because in ResNet, what we have to do is we want to be able to add them together. And the only way we can add them together is if the spatial dimensions are the same and if the number of channels are the same. The number of channels can be made the same by adding a convolution layer, and the number of the the spatial dimension can be made same by adding a stride. By adding a pooling layer. So I hope that answers that question, Ravi. Because if you're concatenating, you're pretty much doing, I think, something similar to DenseNet instead of ResNet. But I'll skip on that. So see on that. So now you can now we can use this res block. I'll take this away. So now you can use this res block, and you can create your learner. You can even pass any stride that you want, even stride 3, but pretty much 2. You could pass in your NI and NF, basically a different, basically any number of channels. And now remember our get model function. So our get model function was Where are you, get model function? Here it is. So now we can still use this. There we go. So you can still use this get model function, but in this case, our block is this res block, right? Because that's what this block function has been defined now, is this res block. So instead of like what we just did was like, instead of creating our block as something which is just one single conf layer, now we've just updated that block to be two conf layers with a ResNet or a skip connection in it, a residual path and a skip path. So we've just implemented ResNet block from scratch, and I could just then do this. I could get my model, and then I could train it, and that's it. And we've implemented ResNet from scratch. And then you'll see one thing that was mentioned in this visualizing the loss landscape of neural nets paper is that what adding a skip connection actually does is that without the skip connection, your loss function looks really, really bumpy, and it looks really, really, now the model has to like go through, jump from here to here. It could get stuck in this local minima. It could get stuck in that local minima. But adding a skip connection actually makes the loss landscape a lot more smoother. So you can see now, instead of like having an accuracy of, I think, what was the accuracy before? About 30s? 65. Okay. Am I doing this correctly? Yeah. But anyway, we are making good progress. I must have made some mistake in training this network, but we're actually now training a deeper network. We're actually now training a network with, we're still training 5 epochs, and we can now make this even deeper, I guess, is the point. So when we get to next week, which is a state-of-the-art ResNet, we're just left with, we're just left with not much, because in this part, we've just implemented ResNet from scratch already. Next week, when you guys come back, we are going to look at the state-of-the-art ResNet, which is like more stuff that you can do, things like mix up, and we will see what a stem is, and we will see like how the ResNet architecture, how like this is the implementation of the overall ResNet architecture. And then we should be able to implement like all of these different architectures. We'll look at a bottleneck layer and what that means. But feel free to read after, because there's not much left. Everything that I've explained today until 1.2.1, we're left with 1.2.2 and 1.2.3, and that's pretty much it. But feel free to read through that. I think it would really be easy for you guys from here on to understand those things. But with that being said, thanks everybody for joining me this week. Please join me for this paper reading group. So we're doing the ResNet live coding from scratch in PyTorch as well. So please join me for this live coding in PyTorch session as well next week. But apart from that, thanks very much for joining me today, and I'll see you guys next week, and bye.